Welcome to our seminar series. Today, the speaker is Nathan. Nathan received his Bachelor of Science in Mathematics in 2002, and it was from the University of Petersburg. And his PhD was in 2009 at University of Southern California. He did postdoc in Berkeley from 2009 to 2013. And he joined us as a lecturer in 2013, promoted to senior lecturer in 2017. And recently, he was promoted to associate professor. Congratulations, Nathan. Okay. Nathan's primary research is in probabilistic behavior of random discrete structures that form the basis of models used in modern statistical applications, such as random networks and gene genealogies. Nathan received the Dean's Award for Excellence in Research in 2017, and he is serving on the editorial board of Electronic Journal of Probability, the Journal of Australian Mathematical Society, and Probability in Engineering and Informational Sciences. Today, Nathan will talk about Gaussian process approximation with applications to Q. Please mute yourself unless you have a question which needs urgent attention. Thank you, Nathan.
Okay, thank you, Ayla, for that nice introduction. And I want to thank the organizers for inviting me. As one of the organizers, maybe I should really just be scolding myself for not having found a speaker for this. So I have to step up myself. Costa says that's called leadership. So here I am, leading from the front. Okay, anyway, so today I'm going to talk about Gaussian process approximation with some applications from queuing. And everything I'm going to talk about today is joint work with Andrew Barbour and Guangqu Zheng. And it can all be found in 2 papers that are on the archive. The titles are listed here, but you can find them. Okay, great. So the kind of results we're interested in are rates of convergence or approximation results for càdlàg processes where the kind of limiting or approximation distribution is a Gaussian process. So the most basic example of this is Donskoy's theorem that we all learn in, during our PhDs or master's degree. What's Donskoy's theorem? It says if I have a sequence of IID random variables, their mean 0 and variance 1, and I look at this sequence of partial sums where we sum up at time t, we sum up basically nt of the wi's, and then scale by the square root of n. So we're scaling time by n. So we're having, steps happen very quickly at rate n, and then and we scale space by the square root of n. And if you do that, that's the good scaling. Then in the limit, this walk as a path, the path of the walk converges in distribution to a Brownian motion. And so this is a very important theorem, because if you can prove some things at the process level, then that means statistics of the walk converge to the analogous statistics of the Brownian motion. So this isn't, I don't want to talk about this result. I just want to say this result so you can all kind of set your mind in the right context. This result is classical. There are incredibly sharp rates of convergence for this available through strong approximations. And so we're working on the setting kind of where these kinds of tools do not apply. Okay, so here's the kind of setting I'm talking about. So here we have a GIGI Infinity queue in heavy traffic. What does that mean? We have customers that are arriving. They arrive at the times of renewal process. So the times between customers is IID. The distribution is according to this random variable R on n, and the mean is m and the variance is v squared of r. And so, writing it as R on n, it's just the rate of these is happening at rate n. And we want to take a limit as n goes to infinity. And so it's helpful to write it this way. But the things we'll talk about will be rates of convergence. So yeah, so you can just think of a renewal process where the rate is increasing quickly. That's the heavy traffic aspect. Each customer in the system is in the system for a random time. And these are independent between customers, and they have the same distribution, which we'll write as the distribution function G, and we'll write G bar for 1 minus the distribution function for the tail probability. So this is infinity queue, meaning there's infinity servers. And so as soon as the customer arrives, they get served for a random amount of time. All right, we'll denote YNT is the number of customers in the system at time t, and XNT is just like in Donsker's theorem, we'll have to center and scale everything. So we subtract the mean from YN and we scale by the square root of n. There's some constant scaling here just to get the formulas a little nicer, but that's not that important. That M and that V are coming from the inter-arrival distribution. Okay, so then the result is as n tends to infinity, this process converges in distribution to Z, which is a centered Gaussian process with covariance given by this formula here. So I'll discuss it in a little bit. The key aspects, I should say, so this result, the convergence result goes back to A. Borovkov from 1967. These kinds of processes and related ones have been worked on since then a bit. So Ward-Witt did a bunch of things in the 80s and 90s and even in the 2000s. And then there's some more recent work, people have revisited these kinds of models. Okay, so this covariance, the interesting features of this are, firstly, it depends on G. So if I change this service distribution, then the covariance totally changes. That's the first thing. The second thing is I've written it this way because this is a covariance function, and this is all, and the thing on the left is also a covariance function. And so you can write Z as Z1 plus Z2, where they're independent Gaussian processes. This one is just by looking at it, you can see it's an integral against Brownian motion, stochastic integral against Brownian motion. This one, unless G is exponential, unless the service times are exponential, this isn't even a Markov process. So as long as the service times are not exponential, this limiting process Z is not a Markov process. And so all the kinds of tools from standard tools from stochastic calculus and stuff don't really apply. So this is really a Gaussian process and not like a diffusion with Gaussian marginals. Okay, good. So this is so we're interested in a rate of convergence here, and this is our result. So part of our results. So we provide rates of convergence for this limit theorem. So the assumptions you can take for this talk. We have more general, weaker assumptions, but the bounds get more complicated. So to make things simple, just have this in your mind. Either the inter-arrival distribution, that R distribution that we're scaling by n, it either has integer support, and we assume it has at least 5 moments, or it's exponential. Okay. And then for the service distribution, we'll assume it's Lipschitz. So you can think of it as having a bounded density or something like that. That's fine. Again, we can sort of weaken these things, but the bounds get more complicated. All right, so now what do our bounds look like? So the first bound is not at the process level. We have a function f from Rk into R. It's bounded with 3 bounded derivatives. And then for any of the finite dimensional distributions of at k times, t1 through 2k, where k, the last one is less than or equal to big T, the expectation against this kind of smooth function of the marginals of the process compared to the expectation of the same smooth function against the limiting Gaussian process is bounded by this quantity here. So the quantity has a constant that depends on f, the function. The way it depends on f, the function, is just in the bounds on the derivatives in the bound of the function. It depends on R and depend on R through the moments, things like that. But the reliance on T, the time horizon, so we're kind of thinking of just looking at the process up to time big T, is completely explicit. The reliance on the dimension K is completely explicit, and the reliance on the rate of arrivals is completely explicit. So here, this is nice because you can let K grow with N, you can let T grow with N, and this bound may still go to 0. So you can actually get better bounds than just fixing kind of K and times and sending N to infinity. Okay, again, that's not process level, that's just finite dimensional distributions. This is sort of telling you the distance between the finite dimensional distributions, the distributional distance between the finite dimensional distributions. And so at the process level, we have the following, assuming R has all moments finite now, then for any chi bigger than 0, we can look at the Levy-Prokhorov distance between the process xn restricted to the window 0t and the process z restricted to the window 0t. That Levy-Prokhorov distance is bounded again by a constant that's going to depend on the distribution of R, and it's going to depend on chi. but the dependence on t, the time horizon, is explicit, t to the 2/5, and the dependence on n is n to the negative 1 on 20 plus this little chi. So as chi goes to 0, this constant will blow up, but for any fixed chi, we can get this rate. So we're getting almost n to the negative 1 on 20. That's what we're getting. Okay, so these are the kinds of bounds we get. We have other bounds, but let's just talk about these bounds today. Good. Okay, so then for related results in terms of rates of convergence in these, we don't really know of any except for some recent work by these two teams, or two closely related teams, and all of their work is for the Infinity Q, and that case is a bit easier. In that case, you do have that exponential service distribution, and in the Infinity Q, the limiting Gaussian process is an Ornstein-Uhlenbeck process. So things are a little easier, basically. And their results don't really seem to generalize to the setting that we're in. But I will say that in the Infinity Q, they're getting results that are better than ours, rates that are better than ours. But we're aiming for something more general. So it's just sort of a little different angles there. Okay, so I'm going to spend the rest of the talk sort of talking about how we get these results. There's sort of three big ingredients. The first thing we had to do, we developed Stein's method for Gaussian processes in kind of a high level generality. There was some Stein's method for some Gaussian processes, Brownian motion, but we're doing it at a quite high level of generality. The second thing is when you develop Stein's method for some distribution, you need to kind of harness the Stein's method, and that'll depend on the application. And the way you do that depends on the applications. In our case, we have to develop Stein's method using palm couplings. So Stein's method for Gaussian processes, where in the application you're using palm couplings. So we'll talk about that. And then the final thing is, typically when we're working in these things, those two steps only give us something for smooth function metrics. And in order to get to a bound on, say, the Levy-Prokhorov distance, which is more of, it's not a smooth function metric, you're looking at the differences of probabilities of sets, right? The probability that this process is in some set minus the probability that process is in some set, those are not expectations of smooth functions at all. We need to do some smoothing inequalities, so infinite dimensional smoothing inequalities. That's something we had to develop. Okay, so that's what I'm going to do. So the way I'm going to do this is I'm just going to go through these three steps in the case of the multivariate or even univariate Gaussian, where things are simpler and more familiar to people. And then I'm going to go through it again at the process level and sort of tell you where the differences are. Okay, so that's the plan. We're going to go through these three steps twice, and it's only sort of 2 slides per step. So hopefully just keep the 3 steps in your mind. Yes. Okay, so the first step is to develop Stein's method for multivariate Gaussians. We need Stein's lemma. Stein's lemma says that if you have a d-dimensional random vector, that it is centered Gaussian with covariance sigma, where sigma is a matrix, if and only if for sufficiently many functions f, you have that this expectation of this operator a sigma applied to f against w, which is given by this is what a sigma is doing. A sigma is what's in the expectation here, if that equals 0. So what that says is if you have a w and you plug it into this thing generically and it equals 0 for enough functions f bounded with 3 derivatives, something like that, then it must be Gaussian. And then, so because of that, we call a sigma the characterizing operator of z sigma, which is the multivariate normal 0 with a covariance sigma. For obvious reasons, we call it the characterizing operator. Okay, so that's the first step. This is going to play the role of like the characteristic function in the sort of classical approach of reconvergence. Okay. All right. So the next step is going to look a little weird now, but I'm just going to say it because, and then I'll explain it on the next slide. So the main theorem here is that if we have a function h from Rd to R, and it's bounded with 3 bounded derivatives, then I can define this function fh of w. W is an Rd valued thing. That's basically this integral of an expectation of h against something involving w and the z sub sigma, and there's a variable t here. We subtract the mean here, and then we integrate against t. So that's just, I'm just going to call that, I'm going to define that as a function. That's a function. You can show it's well defined. I'll explain why in a second. But the key thing about this function is it solves this equation. So when I take a sigma fh of w, it solves the equation h of w minus the expected value h of z sigma. Okay. that's the key thing. So this theorem is very key. It's not clear why right now, but it will be in a second. But I want to put these on the same slide because the way to think about this in more familiar terms, if you're not familiar with Stein's method, is if you look at this, you might think, oh, this A sigma, you know, the thing in the expectation here, this looks like the generator of a diffusion process, right? We have these mixed partials, second partials. We have a, you know, we have this kind of drift term coming in, and you would be right. This A sigma is the generator of an Ornstein-Uhlenbeck process. Okay, so that's what that is. And moreover, that Ornstein-Uhlenbeck process has a unique Gaussian stationary distribution, Z sub sigma, or this multivariate normal. And so, you know, if you know your Markov process theory, if you have a, you know, nice Markov process and it has a stationary distribution, expectations of the generator of that function against the stationary distribution are 0, and that actually characterizes the stationary distribution. So you can think of Stein's lemma in that way as a kind of Markov. That's a kind of Markov process way to think about it. And then this theorem, what's happening here is this term here is actually the semigroup. This is an expression of the semigroup for the Ornstein-Uhlenbeck process. So if I start the process at W, at time t, the distribution of the Ornstein-Uhlenbeck process will be the same as this argument here in H. Okay, and that's the so then this is some expectation of the semigroup, and so then this theorem is just some Dynkin formula. Okay, so if you know what a Dynkin formula is, that will mean something to you. If not, don't worry about it. That's this is just one way to think about it if you're familiar with all these kinds of concepts. Okay, so this is a theorem from before. It's exactly the same. We have some FH of W. We've defined it in this funny way. It solves this equation. Why does that help us? We want to compare the distribution of some vector x to the distribution of z. So we have some d vector x, it's random. And if what we do is we plug in x everywhere there's a w, so we have x, and then we take expectations of both sides. And what we get is the expected value of this is equal to the difference of these expectations, right? And so if we want to compute the right-hand side, which is a measure of how close the distributions of x and z sigma are, right? If I can say that the expectations of enough test functions are, the difference of expectations of enough test functions are small, then the distributions will be close. So that's what we're looking at the right-hand side. And instead, we can just bound the left-hand side. And the reason that that's useful is the left-hand side does not have z showing up in it, right? That's just got x's, or here w in this formula, like the Gaussian manifests itself in the covariance structure. That's all. Okay, that's great. So then we want to bound this thing. How do we do it? Well, we're going to have to use the structure of x, but also f sub h. Just looking at this, you can see f sub h is going to inherit kind of smoothness properties from h, so derivatives and things like that. If I take the derivative with respect to w over here, I can push it, I'll push it through the integral, and I get a derivative with respect to w over here. And each time I take a derivative, I kick off a power of e to the negative t. That's basically what's happening. So, so if we assume h is smooth, we get that f sub h is smooth. And so that's what we do. We're going to bound this quantity by Taylor expansion and using the structure of x. Okay, and I should say this perspective is called the generator approach. It's fairly standard by now. Well, it's developed, but maybe not standard by now. And it's due to Barbour in 80s and 88 and 90. There was a paper for Poisson process approximation and for some Brownian motion type approximation, and Goetze wrote a paper for multivariate normal. All right, so this is yeah, kind of a thing exists. Okay, and this is what we want to do. Remember, we want to bound this expected value of a sigma fh of x. So let's assume d is 1, so we can get rid of all the partial derivatives and make things simple. And let's also assume, because this is what our setting will be in the future, that x is of a certain form. The form of x is y minus y's mean divided by standard deviation, where in particular y is bigger than or equal to 0. So y is counting something. And that's going to be our setting. Remember, y sub n was the number of customers in the system at time t. Yn of t was the number of customers in the system. So in the process level, y will be non-negative, and then we centered it and standardized it. So x has this form, and what we want to bound is this expectation, a1 f of x. A1 here is because I had the sigma before, now there's one dimension, so this is just a standard normal. We want to compare the distribution of x to a standard normal, and this a1 of f of x is just f double prime of x minus x f prime of x, like that. So we want to bound this thing, and we want to bound it for x of this form. That's what we want to do. Okay, so the way to do this is to use the structure of x. Here we'll assume that it has this form, and because it has this form, we'll do a kind of auxiliary randomization. That's what Stein called it in his monograph. And basically, you just want to perturb X or Y here a little bit, and that perturbation allow you to do a Taylor expansion. That's the auxiliary randomization. Here we'll use size biasing because we have a non-negative random variable. What's size biasing? So we'll have a random variable ys. It has the size bias distribution of y if it satisfies this equation. So this equation just means that, you know, y sub s is defined. This defines the distribution of y sub s as being absolutely continuous with respect to y with density y over mu. There's some constructions of size bias distributions for certain settings, but anyway, we don't need to get into that. So size biasing it comes up in a lot of places. It's in the bus stop paradox. You know, if the interval around a typical time of a renewal process is longer than the inter-arrival distribution of that renewal process. So, you know, it takes longer than half the average length of time between buses to wait for the next bus when you just show up randomly. That's the bus stop paradox. That interval straddling a typical time is size bias distributed. The other place it comes up is in sampling. If you know, say I want to figure out how many cell phones people have, the distribution of cell phones, the average number of cell phones. And so what I do is I dial random cell phone numbers and I call up, and then a person picks up and I say, hey, how many cell phones do you have? And then they give me a number and I record all those numbers and I say, great, I've got this nice sample of numbers of cell phones. But that's not like a random sample because I didn't choose a random person, I choose a random phone, right? And so if a person has 5 phones, they're 5 times as likely to be called. And so the distribution of numbers I would have written down in that sampling scheme would be size bias distribution of the true distribution of the number of cell phones. Okay, so it's a very cool distribution. It comes up in a lot of places. All right, so if we write x, how does this help us? So x is equal to y minus mu. We're going to write xs. It's not the size bias distribution. This is abusive, but we'll write it as the size bias distribution minus of y minus mu over sigma. Now, when we look at the expected value of x f prime of x, well, we expand this, we have x and we have a y minus mu. And so we get a y f prime of x and a minus mu f prime of x and all divided by sigma. So this minus mu f prime of x is sitting here, these two, mu f prime of x. And then we have a y f prime of x, but we can think of f prime of x as just g of y, right? Because x is a function of y. So that's just g of y. And so we can use this relationship. We have a y g of y, and so we get a mu g of ys. And y is sitting in here in this x, and so we get an f prime xs there. And so then we get a factor of mu coming from here, and this is where this comes from. And now we're in business, because what we want to do is we need to somehow match this term. We want to say that this thing is close to that, okay? And what we've shown is this thing equals that, and now we have the difference of derivatives. We can do a Taylor expansion about x of f prime, and you just get this thing over here. So you get f prime, you take the first derivative, the difference of xs and x is ys minus y, and we pick up another factor of sigma. All right, and then this is the third order term here. Now we have a sigma cubed, we get the 1/2 because it's the second derivative of the first of f prime. And then this x star is just some random x, it's just some random quantity between x and xs. It depends on x and xs, but it doesn't matter, it's not going to matter. Okay, so now when we look at this difference, we can compare it to, we should take this minus all this stuff, and we match this term to that term. And one thing you can check just by this relationship, the size bias relationship, is the expectation of this is sigma squared over mu. So mu over sigma squared times the expected value of ys minus y is 1. So that really will match well with this thing. And so we'll get a variance term when we do that. Okay, so you combine all this stuff and we get a bound on the Wasserstein metric. So what's the Wasserstein metric? The Wasserstein metric is between x and this standard normal. It's the supremum over all Lipschitz function with Lipschitz constant 1 of the difference in expectations of x and the standard normal. Okay, so that's what you look at that thing, you go and you chug through the stuff we did above, and you'll get this inequality. This variance term is coming from matching that f double prime term. This next term with the squares is coming from the third order term. Well, it's the second order term of f prime, right? Okay, so that's all this really is. So, you know, there's a lot of details here, but it's really quite straightforward from the previous slide. Okay, good. So in order for this to be good, we need ys to be, I should say, okay, we're thinking of a sort of central limit regime where mu is like order n or something, and sigma squared is also of order n. So this is constant order. And so we need this conditional variance to go to 0. This thing right here, mu on sigma cubed, is sort of already 1 on order square root of n, the kind of central limit regime. And so all we need is ys and y to be bounded in this L2 sense, right? That's all we need out of that. So this is typically the harder term to show because you really have to match the conditional variance to its mean. Right? So the conditional expectation to its mean. But anyway, this result, which is due to Baldi, Renault, and Stein, essentially, it gives optimal rates in many applications. Optimal meaning you get this, well, optimal rates, I'll just say. And this is, for example, counts in random graphs or allocation models where you know, balls and bins type models and stuff like that. So there's a whole book about normal approximation by Stein's method, by Chen, Goldstein, and Shao, and they would have lots of examples of this or applications of this. And there's also a you know, we specialize the D equals 1, but there's also a multivariate version of this. All right, great. Okay, so that's step 2 we've done Stein's method. We've now harnessed the Stein's method by using size biasing, this structure of X. And now what was step 3? Well, see, we have this funny metric, this Wasserstein metric, but we want to compare the probabilities of X to the probabilities of the standard normal directly. This just tells us about some expectations of functions. How do we do that? Well, for that, we use smoothing inequalities. Okay, there's a whole bunch of different smoothing inequalities. I'm going to use now a suboptimal one, but that's because for what's coming, we will need that same one. Okay, so one type of smoothing inequality is Gaussian smoothing. Okay, so we have a smooth test function, Wasserstein bound, and we want to bound this. This is what we want to bound for generic K, the probability X is in K minus the probability of standard normal is in K. How do we do that? Well, what you do is you think of this as an expectation of the indicator that X is in K, and then we're gonna perturb that indicator to make it smooth. So how do you do that? You take a standard normal, Z prime, and well, so any questions? No? Okay. You take a standard normal Z prime, and we're also going to do a thing just to save a little space here. We're going to write K to the gamma, K is a set for the gamma enlargement. So that means we take all the stuff within gamma of any point in K. Okay, so we enlarge K a little bit. This will just show up somewhere. It doesn't matter too much. And we'll define this function H delta gamma of X. X is a number. And this is just the probability that X plus delta Z prime, the standard normal, is in this K, this gamma enlargement of K. And when we do that, what happens is this thing is just standard, or this thing's now just altogether is just normal. Its mean is X. Its standard deviation is delta. So it has a density, and we can just write it. We can just write it like this. Right. And now the reason that that's so helpful is now this thing is smooth in X, right? Because now I've got this density here. This is a nice smooth density. When I differentiate with respect to X, I just push it through the integral and I can differentiate with respect to X. So this is kind of a smooth version of this indicator X in K, of the indicator X is in K. And you can see, so you can check H delta gamma, it's bounded, infinitely differentiable. Its derivative is in absolute value, is bounded by 1 on delta. And that makes sense. Like when delta goes to 0, the derivative should blow up, because as delta goes to 0, we're getting back to that indicator, which won't be differentiable, right? And so, and this is the proper rate that it blows up. And so you can then bound the expected value of H delta gamma of big X now, and the same expectation with respect to the standard normal by 1 over delta times the Wasserstein distance. That's because if I multiply delta over here on the left-hand side, I get something Lipschitz 1 that's bounded by the Wasserstein distance because of the definition of the Wasserstein, and then I divide the delta to the other side. Okay, good. How does that help us? All right. So I put the carriage before the horse or something. But again, the idea is that this is going to basically, this function kind of approximates this one, where I replace little x by big X. And so now we just need to take care of the error we made in swapping the indicator for the smooth version of the indicator. Okay, so this is just the definition of H gamma delta, same. And here are the key facts. The probability that X is in K is upper bounded by the expected value of this H delta gamma of X plus the probability that this Z prime in absolute value is bigger than gamma on delta. Why is that? We just write this event, we split it across this event and its complement. But if X is in K and we're in the complementary event where Z prime is less than gamma on delta, then X plus delta Z prime must be in the gamma enlargement of K, right? X was in K, Z prime times delta is less than gamma, so we can't get out of the gamma enlargement, right? And so that's going to give us this bound. And then for this bound, well, you know, I just, over here, I had the probability X is in K and this occurs. And so I just throw away that event that X is in K. Okay, so we get this bound. this upper bound. And this is allowing us to compare this probability to our smooth version probability at the cost of this, at the cost of this Gaussian tail probability. Okay, and we're thinking of gamma and delta as both going to be small, but we're going to need gamma over delta to go to infinity in order for this term to go to 0. Okay, and then you can do a similar thing the other way. If I look at h gamma delta, then I can sort of enlarge it by another gamma. So I get a 2 gamma and plus the same probability. So this really is exactly the same argument as this thing here. Okay, and then altogether, we want to bound the probability x is in k minus the probability z1 is in k. And so we use the first inequality. This thing is less than that plus one of these. Then we want to use the Wasserstein bound from before. So we subtract this thing and we add it back on. But when we add it back on, we use this inequality. And so that gives us another factor of this probability. And then we get this thing minus the probability z1 is in k. And so we get this all together. So that's it. This is how you do these smoothing inequalities. Okay, and then from before, this thing was bounded by 1 on delta times the Wasserstein distance. This thing is gamma and delta are both positive. We just use the Mills ratio. We get this thing, we get this exponential upper bound here, and this one stays the same. Okay, and then you can get a lower bound by doing the same kinds of tricks. And when you do that, you now have to balance terms. You have to choose delta and gamma and in terms of the Wasserstein distance. And when you do that, you can write everything in terms of the Wasserstein distance, and essentially you get the Levy-Prokhorov distance between x and z1 is bounded by some constant that's easy to compute, but I just didn't write it down, times the square root of the log of 1 over the Wasserstein distance times the Wasserstein distance. So typically in the central limit kind of theory, the Wasserstein distance setting is the Wasserstein distance is 1 on the square root of n. So this is the square root of that. We'll get 1 on n to the 1/4, and then we'll get a square root of the log n. So the rate will be square root of log n over n to the 1/4. That's not going to give us an idea. That's typically not going to be a good rate, but or not a good rate, optimal rate, but it gives you something. Okay, good. So that's how it all works in one dimension, and we can do this smoothing you can do in multiple dimensions. You just add a little multi-dimensional Gaussian. So that's how it all works in multi-dimensions. So how does it work at the process level? It's quite similar, actually. So first, let's just set our setting. We're going to work on the space D of càdlàg functions that are on the time horizon 0t into R, and we're going to equip that space with the soup norm. That's a Banach space. And so, so if we have a function from D to R, we have a notion of Fréchet derivative, right? So you have a notion of Fréchet derivative on a Banach space, and so we have df. We'll write those things df, d squared f. So what's the Stein's lemma analog in process level? Okay, W in D has the same distribution as the centered Gaussian process Z hat here, if and only if for sufficiently many F, the expected value of this operator A Z hat, it really only depends on the law of Z hat, but that's why I'm writing it, it's just a little abusive, F of W, which is defined to be this expectation is equal to 0. And I should say in this expectation, I'm being a little abusive here, the Z hat is gonna be independent of W. Okay, that's the idea. And this operator A, if this was a little w and not random, there'd be no expectation on this side, and this expectation would be just against those Z hats, and there'd be little w's here. So I'm being a little sloppy, but anyway, that's what this is. You can just think of these things as being independent. Okay, how does that compare to the finite dimensional setting? Well, it's the right thing. I mean, if we wrote exactly this, but Z hat was now finite dimensional, it would be like a bunch of coordinates. And when you take derivatives against infinite dimensions in some direction, you just sum over the partial derivatives times the coordinates of those directions. So here, this thing would be without the expectation, this thing would be the partial in ij, f of w, and then we'd have a zi, zj here, or z hat I, z hat j. And then when I take expectation, that just turns into the covariance. And so that just turns into covariance, and that's exactly the right analog. But I will say there's a problem here. The problem is we don't want this in here. We don't want the actual process sitting around. We just want the covariance structure of the process sitting around in order to bound this thing, because that was the whole point of doing Stein's method, was to avoid having to put the processes or compare the processes directly. Okay, good. So that's the analog. It looks like the right thing. Okay, so again, this is just sort of almost repeating exactly what was happening in the finite dimensional case. We have a, once you have the Stein's limit analog, now we look for this Stein solution. So we try to look for a solution. We apply this operator to some function, and we want that to be equal to h of w minus the expected value of h of z hat here. And well, the solution is exactly the same form. It's just now w is càdlàg valued. And this is still sort of thought of as like the Ornstein-Uhlenbeck-Semon group, but we don't actually use any of that language because it's very hard at the process level to define a Markov process on processes. So once again, the way we prove this, we just define this thing, and then we show directly using, kind of really nice properties of Gaussian processes like, orthogonal expansions and stuff, that it satisfies this equality. And so that's sort of the better way to do it than to go through this Markov process setting, or these Markov process results, which sort of you always think will save you, but never actually apply to your application. So anyway, okay, so then we do exactly the same thing. We put a random process in here and take expectations, and so we find that this expectation of this thing on this left-hand side still sort of has a z hat in it equals this expectation, and this is what we want to bound the difference between. So now we need to work on bounding this thing. Okay, so good. So before then we could move directly to the auxiliary randomization and work with just the structure of X. And and I should say there's still smoothness being sort of inherited here. When I take derivatives here, I sort of push them through and I get derivatives of H, right? So so really we will have a Taylor's theorem at the functional level and everything. So so we need to bound this, but we're going to have to take a quick interlude to deal with this term and get this to something that looks a little nicer. Okay, so this is just a quick reminder. Remember back at the beginning of the talk, we had the GIGI Infinity Q and heavy traffic. I'm going to start using this notation again. So we have an interrival distribution, R on N. R was fixed. It has some fixed mean, some fixed variance. Service distribution had a function, distribution function G, and yeah, YNT is the number of customers in the system at time T. XNT is this centered and scaled version of YNT, and XN converges in distribution to this Gaussian process with this covariance. Okay, so now we're back in this setting. Our results are general, but I just want to make things concrete. Okay, so the first thing is we can actually write this in a slightly different way. For the target Gaussian process Z, a simple calculation gives that the covariance can be written as a integral. The integral is against just Lebesgue measure, and then G dy. G is the service distribution. Okay, and what it's a bit funny, like these K's, KSY, for each SY, KSY is a function, and the T1 here is coming, depending on the covariance here. Okay, the covariance of the times that we're going to look at. And for each KSY, we have this expression. Okay, you don't need to look at this too much, only to see that it's very simple. M over V times some indicator, M plus V over V times G bar, some indicator, very simple, bounded, easy to deal with. Okay, and the theorem here is that when I look at the expected value of this problem term, where I'm taking the derivative in the direction of the Gaussian process, that has now a deterministic form, which looks like this: d squared f of w, ksy, ksy, and then I integrate over s and y. You can almost see, I mean, it's almost obvious, right? Like, I plug in this expectation, nothing here is random, so I should sort of push this expectation into there. And when I do that, I should get kind of the integral ksy, dsg, dy, and then I should be able to pull the integral back out, right? Because, derivatives are linear and everything. So the integral is sort of in here, and then I pull it out. Okay, that's what, so you guess this, you can guess this formula from the structure, but there's work in making sure all these things, all these integrals and derivatives, actually, you can do these manipulations. Okay, so that's the theorem. And then, then that's great, because now we're back on very familiar looking territory. We want to bound this thing. This will give us a bound on the distance, on the smooth function distance between Z and X. And it has this form. We have our nice derivative of X in the direction X here. Here's an X sitting here with a second derivative. And so now we need to work on X. and do some auxiliary randomization and do a Taylor expansion so we can find a d squared term to compare to this d squared term, just like we did in the size bias. Like we do the Taylor expansion, then we have something to compare to. Okay, so that's what that is. Okay, good. And so how do we do that? Well, we need some special structure of X to decide how to do the auxiliary randomization. So for the GI, for this queuing process, YN, we're going to do some analog of size biasing. One analog of size biasing at the process level is something called the palm distribution. But for that, you need a point process. So let's get a point process. We write Ti of n, comma Vi. This Ti of n is the time of the arrival of the ith customer. So these TIs are increasing. And Vi is the service time that the customer has. We can just collect those, right? The customers are coming in, they get some service time. We just write those down, they're random variables. And we define a random measure or a point process, n sub n. And this is just the point process where it's in R2 and we put a point in R2 exactly where a customer arrives, where the X values is their arrival time and the Y value is their service time. And so we just get this point process of all the arrivals of the arrivals and service times of all the customers. That has a mean measure that we'll call lambda m. That mean measure is essentially n over m ds g dy, which is coming from, in renewal theory, like the time between renewals has mean m, then the rate of arrivals is 1 on m. So we have the time between these renewals is m on n, and so the rate of arrivals n on m, and then the renewal theory tells us that they in the limit they look like the big measure. So that's where this is coming. And then this GDY is because the service times are independent, and that's good. You should be thinking that's already quite good because now that's something that was showing up here, right? It's showing up here. So if we do some expansions over here, we pick up this ds gdy kind of terms. We have some hope of doing that, I guess is what I'm saying. Okay, so we do all that. Now what? Now we want to write ynt. Ynt we can write as an integral against this point process, or you can just think of it as a sum because it's a simple point process. Against these JSYs, what's JSY? It's the indicator that at t, it's the indicator that s is less than or equal to t is less than s plus y. So you see, if we have an arrival at sy, it will be in the system at time t if, well, firstly, its arrival time was s, it has to be before time t, or at least time t, right? In order to still be in the system at time t, and it's the time it leaves the system, which is s plus y, has to be less than or equal to t, right? So that means, or sorry, greater than t. Excuse me, yeah. I have a picture that explains this all much better. Okay, so this is what I just had before, but here's the point process of service and arrival time. So the y-axis is the service time, the x-axis is the arrival time. At time t, who's still in the system? You see, if I have a point here that arrives here at some time, when does it leave the system? Well, it's in the system this amount of time, so I just draw a 45-degree angle, and that's when it leaves the system. So every arrival above this line and to the left of this line is in the system at time t. So all the blue arrivals are still in the system at time t, and all the reds are already gone. And that's essentially what this decomposition is doing. So we're just integrating this point process over these kind of trapezoidal type regions, right? That's what we're doing. That's all this is saying. Okay, good. So how does that help us? All right. This is I'm going to go through this fairly quickly because it's just a little too technical, but it really matches well with the size bias. So just keep the size bias in mind. We want to bound this term, and we'll focus again on this term, dfxn of xn. Xn is y minus its mean divided by sigma n. Yn has this form here. We're going to define this thing called the reduced palm distribution. So we'll say we have these random variables and u is in r plus 2. So you want to think of u as sy, but I couldn't write sy because the formulas got too long. That has the reduced palm distribution of n sub n. That means it satisfies some, characterizing distributional kind of equation here. Don't worry about this equation. What you want to think of n sub nu is that you condition n sub n to have a point at u, or sy, and then you look at the rest of the process. What's the distribution of the rest of the process? So n sub nu has to have that distribution, and we need to couple it to the n sub n's for every u. So for a simple Poisson point process, n sub nu is the same as n sub n, right? Because if I condition to have a Poisson point process to have a point somewhere, it doesn't change the rest of the distribution because of independent increments. Okay, so that's what you can think of, and then we can write YNU to be the same integral here, except now we're going to integrate against the Palm measure, or the reduced Palm distribution, and or random variable, and then we'll let XNU to be the YNU minus the mean over sigma n. You know, like this is exactly an analogy to the size bias case. And you can then do, I'm not going to explain it in detail, but it's really the same idea. You can do exactly the same thing. When I write x sub n, I write it in the direction of the derivative. I write it as yn minus the expected value of y sub n divided by sigma n. That gives me that. And then that derivative is linear, so I can split it apart. And on the one hand, I get dfxn at expected value of yn, which is just going to give me this term. And on the other hand, I'll have this yn times dfxn, and you can write it in this form on the left-hand side, and then turn it into this form on the right-hand side, and that's what this looks like. So this gn nu plus delta u corresponds to this thing. Okay, I don't want to get into it too much. But if you sit down and just write down these definitions, it's actually quite easy to do this. And now we're in business because now we have a difference of two derivatives, and we can do a Taylor's expansion and compare the second derivatives to this term here. Okay, and get a kind of analogous theorem to the size bias one. I'm not going to write it down. It's in the paper, but it's not that hard. It's just there's a lot of notation, but the terms are quite analogous in some ways to the size bias one. At the end of the day, we get a general theorem giving bounds on the distance between expected value of h of x and expected value of h of some Gaussian process with a covariance of this kind of form. Sorry, didn't mean to do that. With the covariance of this form that you can write as this integral, like we had with the k's above, and that's for h that are bounded with three bounded derivatives. Okay, and the error bounds or the upper bounds are in terms of this coupling of the Palm measures to the original process. Okay, like I said, if n sub n is a Poisson process, then you can just take the Palm measures to be equal to the original process, and the bound we get is extremely simple in that case. It's very, very easy to compute. If n sub n is driven by a renewal process, then when we do the reduced Palm, like at sy, I'm conditioning to have an arrival at time s with some service y. Well, the service times are IID, so we don't care about that conditioning, but we're conditioning to have an arrival at time s. And so we need to couple the original renewal process back to the process that has an arrival at time s. But that's fairly classical, kind of, those kinds of ideas are fairly classical, how to couple renewal process one in equilibrium to one that's not in equilibrium. You just run them until they meet, basically. And for our case, everything has to be quantitative, so it makes things a lot more complicated. But you go back and you use those ideas, those coupling ideas, and you can get the bounds we have. Okay, these smooth function metrics lead directly to the bounds for finite dimensional distributions. This one I had before. Okay, so we start with the smooth function metric, and then we look at the smooth functions of the finite dimensional distributions, and you can apply this bound fairly directly. Okay, but that doesn't tell us, now we're in this situation we were before. We have this funny smooth bound on smooth functions, and we want bounds on the differences of probabilities. And now, now you have to really think this is messed up. Like, you might be okay in one dimension with Lipschitz functions and what they kind of look like and what they're kind of doing, but like in this setting, what do functions from D to R that are bounded with three bounded derivatives look like? I mean, in terms of natural statistics of the process, it's not clear at all. So what we need to do is we want to move from our smooth test function bounds to one on the difference of probabilities. So I'm writing Z hat here for a kind of generic Gaussian process, because this part will hold just in generically. Okay. So here we know that we have, what we're going to assume is we have some bound on those smooth function expectations of a certain form, and we want to get a bound on this difference for some event k. How do we do it? So let's try what we did for finite dimensions, just for fun. And so if we take B as standard Brownian motion, so what we do is we smooth this by adding a little Brownian motion to it. What happens? We take B as standard Brownian motion, we can define a function from our càdlàg functions to R, h delta gamma of x, which is the probability x plus delta b is in this k gamma enlargement. Okay. Now, is this function smooth in X? The whole point of doing this was to get a smooth function in X. Now remember, X is just a càdlàg function. It's just in D. Delta B is continuous, it's a Brownian motion. Well, in the analogy, what happened is in the finite dimensions, the smoothness of this H delta gamma came from the smoothness of the density of a shifted normal to the original normal distribution. So it came from the density of the derivative of X plus delta B to delta B, okay? So hopefully some of you are probably squirming in your seat that I even wrote this down, because X is just càdlàg. It's not even continuous. And you know, classical Cameron Martin Gersonov tells us that this thing only exists if X is not continuous. It must be absolutely continuous. It has to have a derivative, basically. And so this doesn't exist. And so this is just not going to work. So what do? Well, what we do is, well, you know, we started with something unsmooth, or we started with something smooth, and then we want to smooth it out, or unsmooth and smooth it out. So we add a little Gaussian. Well, let's just smooth the X. So that's what we'll do. So if for X and D, we define this epsilon smooth version of X, this is our function in D, where we add a little, you know, at T, we add a little epsilon times U, where U is uniform between -1 and 1. So we just perturb time by a little random, uniformly random epsilon shift, okay? And then we take that expectation. And because we're smearing this function left and right, this will give us an averaging out. This will be a function that has a derivative, okay? So it's kind of like the Gaussian thing we did before, but I'm only doing a uniform, so we only get one derivative. But anyway, X sub epsilon is absolutely continuous, and it's even, you can even write that its derivative is bounded by, it's of order epsilon to the -1 times the bound here. And so, so that's what we'll do. We'll now doubly smooth, I guess, H epsilon delta gamma of X. This is the probability that this smooth version of X, which is now absolutely continuous, plus delta B, is in this K, this gamma enlargement of K. And then the lemma is that the kth derivative of H, this is the operator norm of the kth derivative, that's what we kind of need. We need bounds on these derivatives, is bounded by something explicit. Again, it's explicit in T, it's T to the K on 2, some constant depending on K, that's explicit number of partitions related to some number of restricted partitions. And then each derivative kicks down in the denominator a power of epsilon and delta. Okay, and so why does this hold? So this is kind of neat. Well, the idea was just like back here, we want to harness this smoothness of the derivative. So we use the Gersonov change in measure, and that implies that this thing, we can switch, change measure from X epsilon to delta B with this change of measure, and under the change of measure, this thing becomes just delta B, right? Because delta B is absolutely continuous with respect to this, or both. And yeah, so we write this change of, we do the change of measure, we pick up this e to the psi of X, and psi of X has this form, that's just the Gersonov form there. 1 on delta, indicator 0t, X epsilon prime of T, dBt minus 1 on 2 delta squared integral 0 to X epsilon prime of S squared ds. And then informally, what happens is you see here's X, there's no X here. So when we differentiate, we're just differentiating this thing with respect to X. So we have e to something. And so when we differentiate with respect to when we differentiate this thing, we can push that through the expectation. We're just going to differentiate this exponential term. And then, you know, when you differentiate an exponential term, you get the exponential term back times some polynomial of the derivatives of the thing in the exponent. And that can be written in, you know, combinatorial ways using Claude de Bruno's formula. And but here it's quite simple actually, because the first derivative, you can write it explicitly this way. It's a bit weird because the first, you know, this is all very heuristic, because the first derivative is like a random variable. It's like a stochastic integral here. But the second derivative is actually not random. It's just given by this. There's no b, there's no x in it even. So then all the higher derivatives are 0. So there's only 1 and 2 derivatives sitting there. And the first derivative depends on x via this b minus delta inverse x epsilon, which under the change of measure comes back as distributed as b. So this thing is really, once we undo the change of measure, this derivative turns into this stochastic integral against a Brownian motion. And so this thing has order square root of t, because we're integrating from 0 to t. There's a delta down here in the denominator, and the 1 over epsilon coming from this thing. coming from this when you kind of look at the bounds. So each time you pick up one of these derivatives, you get a 1 over delta epsilon squared root of t. And for the second derivatives, this thing's of order t, and you get a delta squared 1 over epsilon squared from this. Okay, anyway, it's kind of neat the way it all works out. There's a lot of details there, but it works out very similarly. And yeah, okay, so then we can just do similar to the finite dimensional case, but we do need to account for the new error coming from switching from x to x epsilon. And at the end of the day, we get this bound. If we write d smooth for the implicit smooth function metric of our general theorem, then when we look at the absolute difference of probabilities between our x and our Gaussian process, you get some constant divided by epsilon delta cubed times the smooth function metric plus this is the cost of replacing big X by X epsilon, and this is the cost of replacing Z by Z epsilon. And you have to look at how much that changes. This thing is basically like the modulus. This can be written in terms of the modulus of continuity of X. And so, so these terms showing up, they have something to do with like tightness in some sense, because you need the modulus of continuity of X to be well behaved in a certain sense. That's going to come into play. And then here, there's some other terms that are completely analogous to the one-dimensional case. So it's worth comparing this to the one-dimensional case. Like everything is basically this, like these terms are basically exactly the same as those terms, because we're doing it exactly the same way. This term is replaced by the 1 over delta times the Wasserstein, but that's because the Wasserstein only uses one derivative. If we were using a 3-bounded derivative metric, we get a 1 over delta cubed, and then everything else is just coming from that changing from x to x epsilon.
Can you finish in 2 minutes or so?
I'm totally done. Yeah. Okay. Anyway, there's more results in the paper. It's you can take a look. We can do this all in the multivariate case. The queuing applications, there's more general conditions and stuff. And then we also talk a lot about bounding these modulus of continuity terms coming up here, because they're kind of a hassle. But again, it's quite classical because these are related to classical criteria for tightness. Okay, thank you very much. Sorry for going over.
Okay, that's okay. Thank you very much. Questions, comments?
Kasia, are you going to tell me that these rates of convergence are like already known from, you know, the Soviet literature in 1985?
Yes, everything is well known. It was done long ago by the Kiev school.
Yeah, so this is exactly my comment, nothing. So I just let me share, or I can't share my screen, so I am not the host. So I just was going to show you the inequality. Can I do it now? No. Okay. So we use similar inequality, but you use like a smooth version. There is an inequality for general random variables. Maybe you can look, I will send you link. So we published paper in Bernoulli about that. So a distance between probability distributions. So maybe it would be useful. I can't tell that it works for processes, but in the first case, definitely there is much more general result. Probably you can extend this to more general settings.
Oh, you're saying in the not for the processes, for the
yeah.
So well, please send me the paper. I'm actually quite interested in it. But no. I present that's the worst way to do it, basically, using the Gaussian. Like it would be better to use uniforms even, because then you wouldn't have that extra Gaussian term showing up. But you can even in RD, you can do this kind of sandwiching, you know? So I presented it that way. That's totally suboptimal, but I just did it that way because it matches what we have to do in the process level. Like we don't know an analog of these better kind of smoothing inequalities for RD. Yeah. So, but anyway, please send me the paper. Absolutely. No. That stuff at the beginning was just motivating, basically. Not those are not good results.
Any more questions? All right.
I have a question.
Yeah, please.
Nathan, would you mind going back to your result? I know it's
the main result.
Yeah, of course.
This one.
Yeah. I'm just reading it, just so.
Okay.
Okay, so the inter-arrival distribution is either has integer support.
Yeah, well, the unscaled integer arrival, so that R distribution.
Right, unscaled. Yeah. Or exponential. Okay.
Yeah, it doesn't have to be exponential. That was just to sort of fit it, you know, in the point process version, that n sub n that drives the that drives the y sub n, you know, the time of arrivals and services, if that's a Poisson point process, our results apply. So
okay, I'm just trying to think with the GIGI Infinity queue.
Yeah,
it's a random delay, and if particularly if it starts empty, I think we know the finite dimensional distributions explicitly.
In the MG Infinity queue.
GIGI Infinity. So if it starts off empty,
yeah,
the distribution, certainly distribution at time t is Poisson.
Yeah.
With a varying time-dependent varying mean, explicit. But I think, I'd guess, although I was trying to think about this, whether we know the joint distribution at fixed set of times.
So yeah, so it would be, because in the MG Infinity queue, the times of the arrivals and services are just a Poisson process. So then those joint distributions, you can definitely write down some expression for by just, you know, just geometrically by kind of looking at these. Let me go to this picture. You know, this is like the number of in the system in time t, the number in the system of time t is the number in this wedge. But if I looked at another time here, I would just get another wedge, right? And those wedges would overlap. They'd be dependent here, but they'd be independent in these regions. Do you know what I mean? Because if this were a Poisson process, the number of arrivals in disjoint regions is independent. So you'd be able to write the finite dimensional distribution in terms of a bunch of Poisson variables, and some would be shared between the finite dimensional distribution. So you could at least implicitly get something like that. So like a fairly good expression that way. But then as n goes to infinity, it's like the usual thing where, you know, you have these weird, you have a lot of sort of correlated Poisson variables, and you're sending n to infinity. So that should be close to a standard normal. So I guess in that case, it is probably fairly straightforward to do it just using standard techniques. But
using calculations, yeah.
Yeah.
And the other thing I wondered is, I was homing in on that integer, taking values in the integers.
That's
inter-arrival distribution.
Yeah, that's more because I don't know if you're familiar with how you do these you know, these renewal type arguments, these coupling arguments for renewal. And so if they're all in the integers, you want to couple a stationary renewal process to a non-stationary one, you just run them till they meet, right? And then that's some finite time, and then they're coupled that time afterwards. And so if they're sitting on a lattice, that's very easy because they can meet. But if they don't sit on the same lattice, if they're continuous or something, the coupling is just really annoying. You sort of discretize the lattice in a certain way so that each time they land close enough to each other, there's some chance that you could then further couple them. And those arguments are just more technical, and it was already technical enough, basically.
Yeah,
but in principle, we should be able to do more general.
I was thinking of practical applications. You're often wanting to keep queues loaded for efficiency, and if with your integer support assumption, you're including this idea of slotted arrivals. So they come in packet switching networks. They come in little packets, of known size. So it works very well. This, if you like, they arrive in
if you sort of check
some number of packets. You know,
you sort of just check you're checking periodically very quickly, right? And so then
anyway,
each time you check, they can show up.
Yeah. Okay. Thanks.
Yeah. Thanks.
Okay. Let's probably stop at here. Let's thank Nathan for the interesting talk. Thank you, Nathan.
Thank you.
All right. So